Okay, page 23, oscillators and resonant systems. We may describe an oscillator as any object that moves in a regular periodic manner. We may call a vibrating string an oscillator, or a weight hanging from a spring, or a pendulum, anything that performs a repetitive periodic movement, that is, vibrates. We may generalize and say that oscillators produce a sound or a note, whether audible or not, as long as they alter their environment in a periodic manner. That environment may be tissue, as in the heart, aorta oscillating system, water, air, electrical fields, gravitational fields, or anything else. Suppose we tune two violins, then put one of them on the table and play a note on the other. If we watch carefully, we shall see that the same string that we are playing on one violin is also humming on the violin that we placed on the table. Clearly, there is a sympathetic resonance between the two. Let us analyze what is happening. When we draw the bow over a string, it vibrates at its own natural frequency, which we call self-frequency. Since the two violins are correctly tuned, we know that the natural frequencies of both strings are identical. Within a system like this, we shall call the two violins a system. It is very easy to transfer energy. In this case, we are talking about acoustical energy. The air waves generated by the first violin impinge on the second violin. The string that is tuned to the emitted note will absorb the energy of the waves of that frequency preferentially, because that energy comes to it as its own natural frequency. The energy transfer within this system is therefore optimum, and such a system made up of two tuned oscillators is called a resonant system. Let us take another example. Suppose we get several old-fashioned pendulum-type grandfather clocks. Let us hang them on a wall and arrange their pendulums so that they will start out beating each at a different angle, that is, out of phase with each other. In a day or two, we shall find that all the pendulums are beating in phase as if locked together. Pendulum length should be the same for all of them. Here we see that the tiny amount of energy that was transmitted through the wall from clock to clock was sufficient to bring them into phase with each other. If we disturb one of the clocks, it will get locked into rhythm quite fast. The larger the number of oscillators within such a system, the more stable the system, and the more difficult it is to disturb. It will force a wayward oscillator back into line very quickly. The sound of the body. The heart is a big noisemaker. We can easily check this by putting our ear on someone's chest and listening to it. Each beat shakes the whole body, and the body has a typical response to this beat, which is quite easily measured. Figure 13 shows what such motion looks like when measured with a sensitive seismographic-like instrument. This movement is clearly related to the heart heat. In fact, the largest peak we see in this graph is caused by the ejection of blood from the heart's left ventricle. The portion between the large peaks looks fairly irregular and is caused by the vibration of the body due to the action of the blood in the aorta, which is the largest artery in our body. This irregular portion is due to a destructive interference pattern set up in the aorta, as will be shown later. When we stop breathing, the irregular signal in figure 13 turns into a nice, regular, practically sine wave pattern, figure 14. This is surprising, and when we look into the reasons for this behavior, we find that the heart-aorta system has become a so-called resonant system, as shown in figure 15, in which the length of the aorta forms 1/2 a wavelength of this system. By resonant system, we mean that it resonates just like a tuned musical instrument. Here is what seems to be the case. When the left ventricle of the heart ejects blood, the aorta, being elastic, balloons out just beyond the valve and causes a pressure pulse to travel down along the aorta, figure 16. When the pressure pulse reaches the bifurcation in the lower abdomen, which is where the aorta forks to go into the legs, part of the pressure pulse rebounds and starts traveling up the aorta. If in the meantime the heart ejects more blood and a new pressure pulse is traveling down, these two pressure fronts will eventually collide somewhere along the aorta and produce an interference pattern. This is reflected in the movement of the body and is the reason for the irregular pattern of body motion in Figure 13. However, when the breathing stops, it looks as if some communication has been set up between the heart and the bifurcation. Some kind of a signal seems to travel from the bifurcation to the heart, saying to it, "Heart, hold it. Hold your next pulse until the echo from the bifurcation returns to you. Only then should you eject the next quantity of blood." When this happens and the echo and pulse move out of the heart together and they continue to move up and down in synchrony, then such a system is said to be in resonance. It causes the body to move harmoniously up and down about it, 7 times a second, hence the nice, regular, large amplitude sine wave pattern in Figure 14. The amplitude or height of this signal is about 3 times the average of the normal signal. Another characteristic of resonant behavior is that it requires for its sustenance a minimum amount of energy. Well, but how long can we hold our breath? Certainly not over a minute or so comfortably, and so we start breathing and ruin the nice rhythmic pattern. Let us not forget now that our body includes our head, and inside the skull, carefully packaged, is a very delicate instrument, the brain. The brain is cushioned by a thin layer of fluid and is wrapped in a tight bag, the dura. About the simplest way to visualize this system is to have a relatively soft, round fruit, such as a peach, enclosed in a can containing a heavy syrup. If we shake the can, we find that the peach will hit the top and the bottom of the can and be accelerated with a small delay in the direction in which the can is moving. This movement is quite small, only 0.005 to 0.01 millimeters. This is exactly what happens to the brain. The question is, how come we are not aware of this happening to us? It's probably because when something is happening to the nervous system for an extended period of time, and that event is not traumatic, it will not be brought to our conscious attention because the portion of the brain that is in charge of censoring and separating meaningful signals from unmeaningful ones will relegate it to the heap of unimportant signals which require no conscious processing. We know from experience that we can easily get used to and disregard the loud ticking of a clock next to us or the noise in the cabin of an airplane. The noise is, however, filed away somewhere and affects us in some subtle ways. If we were to ask the brain how it would like to be treated, whether shaken at a random, irregular rate or in a rhythmic, harmonious fashion, we can be sure that the brain, or for that matter the whole body, would prefer the latter.